At exactly 2:16 and 7 seconds in the morning, Pacific Standard Time, on Wednesday, November 18th, 2026, a spacecraft launched before most of the people currently watching this video were even born will cross the threshold. No human-made object has ever reached before. It will be 16,094,799,096 miles from Earth, a distance so vast that light itself, the fastest thing in the entire universe, will need a full 24 hours just to travel from that spacecraft back to us. NASA has calculated this moment down to the second. Not the day, not the hour, the second. And the fact that engineers can predict, with that level of precision, exactly when a machine built in the 1970s will cross an invisible line in the emptiness of interstellar space tells you almost everything you need to know about both the incredible engineering behind this mission and the increasingly narrow, fragile margin it is now operating within. This is the real story of Voyager 1's approach to this historic milestone, what the spacecraft actually looks like today after 49 years of continuous flight, and what genuinely happens next both on November 18th itself and in the years immediately following it. To understand why this specific moment matters so much, you first need to understand exactly what a light day actually represents, and why measuring distance this way tells a more honest story than any number of miles or kilometers ever could on its own. Light travels at approximately 186,000 miles every single second, fast enough that sunlight reaches Earth in about 8 minutes, and fast enough that a signal bounced off the moon returns to Earth in barely more than a second. A distance of one full light day means Voyager 1 will be sitting so far from Earth that even light, given an entire 24-hour day to travel, would only just barely manage to close the gap. Susie Dodd, the Voyager project manager at NASA's Jet Propulsion Laboratory, has described exactly what this means for the practical experience of actually running this mission, explaining it in the simplest possible terms. If she sends a command and says, "Good morning, Voyager 1," at 8 in the morning on a Monday, she will not receive Voyager 1's response back until approximately 8 in the morning on Wednesday. 2 full days, simply to complete a single exchange of information. 1 command sent, 1 reply received. Voyager 1 launched from Cape Canaveral on September 5, 1977, on a mission originally planned to last only a handful of years, sending the spacecraft past Jupiter and Saturn before its expected retirement sometime around the early 1980s. Instead, it kept going, using the gravity of each planet it passed to accelerate further outward, eventually crossing the heliopause, the true physical boundary of our solar system, in August of 2012, becoming the first human-made object in history to enter genuine interstellar space. It has been traveling through that same interstellar darkness ever since, moving at roughly 37,000 miles an hour relative to the Sun, a speed that sounds extraordinary by any everyday standard, and yet remains almost meaningless compared to the speed of light itself, the actual yardstick being used to measure this particular milestone. It took Voyager 1 more than 49 years of continuous, uninterrupted flight to reach a distance that light itself covers in a single day, a genuinely humbling way to grasp both how fast the spacecraft has actually been moving and how almost incomprehensibly vast the space it has been moving through actually is. Here is where the story becomes considerably less about celebration and considerably more about honest, sober engineering reality, because the Voyager 1 that will cross this threshold in November is not the same fully equipped scientific observatory that left Earth in 1977. The spacecraft launched carrying 11 distinct scientific instruments, each designed to measure a different aspect of the space environment it would eventually pass through. As of the most recent NASA status update in April of 2026, only 2 of those original 11 instruments remain operational: the magnetometer, which measures magnetic fields in the surrounding space, and the plasma wave subsystem, which detects the density and behavior of charged particles drifting through interstellar space. The cosmic ray subsystem was switched off in February of 2025. The low-energy charged particle instrument, one of the spacecraft's most scientifically valuable remaining tools, was shut down in April of 2026, not because it had stopped working, but purely because the spacecraft's shrinking power supply could no longer support it. That shrinking power supply sits at the very center of everything currently happening with this mission. Voyager 1 generates its electricity using 3 radioisotope thermoelectric generators, sealed containers of decaying plutonium-238 that convert heat into usable power as the plutonium slowly breaks down over time. At launch, these generators produced approximately 470 watts of electricity combined. Today, after nearly 5 decades of continuous, irreversible radioactive decay, that output has fallen to roughly 250 watts, and it continues declining by about 4 watts every single year, a slow, mathematically certain countdown that cannot be paused, reversed, or repaired in any way. Engineers at the Jet Propulsion Laboratory have spent years managing this decline as carefully as possible, shutting down heaters, switching to backup thrusters, and combining multiple giant dish antennas within NASA's deep space network simultaneously just to reliably detect Voyager 1's current signal. A transmission so faint by the time it reaches Earth that it now arrives carrying only about 23 watts of power, less energy than a single dim household light bulb, spread out across a signal that has already traveled more than 16 billion miles to get here. This is precisely why NASA's engineering team has spent the past several months working on an experimental power-saving procedure they have nicknamed, internally, the Big Bang, an all-at-once restructuring of how electricity flows through the spacecraft's remaining systems, specifically designed to squeeze additional operational years out of a power supply that would otherwise simply continue its steady, irreversible decline. Because any significant change to a spacecraft's power distribution risks briefly triggering automated fault protection systems during the unstable transition between configurations, potentially shutting down instruments unexpectedly. Engineers first tested this exact procedure on Voyager 2, which currently carries a slightly larger power margin and sits somewhat closer to Earth, making a potential failure marginally less catastrophic to the overall mission. If those tests continue to succeed, the same procedure is expected to be attempted on Voyager 1 itself, carrying with it the genuine possibility that the low-energy charged particle instrument, only just shut down this past April, could eventually be switched back on. It is worth pausing to appreciate exactly what this specific situation actually demonstrates about the nature of operating a spacecraft this old, this far away, and this fundamentally different from anything modern engineers typically work with. Susie Dodd and her team are not managing a machine they can physically service, walk out to inspect, or reload with updated software the way engineers can with almost any other piece of technology still in active use today. Every single decision, every diagnostic test, every attempted fix has to be transmitted across a communication delay that, as of November 18th, will officially reach a full 24 hours in each direction, meaning any single exchange, a command sent, and a response received now takes a minimum of 2 full days to complete. A small error in a single instruction, an unexpected power dip, a fault protection response triggered by something engineers did not anticipate can take days simply to properly diagnose, with no possibility of a repair crew ever being sent to intervene directly, and no realistic way to undo a serious mistake once it has already been transmitted across that vast, growing gulf of space. So what actually happens on November 18th itself, and in the days, months, and years immediately following it? In the most literal, practical sense, remarkably little changes at the exact moment of crossing. Voyager 1 will not suddenly behave differently, and its instruments will not detect anything unique about crossing this particular mathematically defined threshold. The milestone is fundamentally a measurement of distance and communication delay, not a physical boundary the spacecraft itself will register in any way. What does change, gradually and continuously, both before and after this specific date, is the growing operational difficulty of everything the mission team does. Every month, Voyager 1 moves further away, adding a little more delay to every future command and response. Every year, its power supply loses another 4 watts, forcing engineers to make increasingly difficult decisions about which of its few remaining functions to preserve and which to finally, permanently switch off. Based on current projections from the Jet Propulsion Laboratory, Voyager 1 is expected to continue operating in some capacity into the early 2030s, before its power output finally drops below the minimum threshold required to run any of its remaining instruments at all. When that moment eventually arrives, the spacecraft will not simply stop existing or suddenly vanish. It will continue moving outward through interstellar space exactly as it has for the past decade and a half, at the same steady speed, along the same, essentially unchanging trajectory, just without the ability to transmit any further data back to Earth, or to receive and respond to any further commands sent to it. It will become permanently silent, a machine still physically intact and still moving, but no longer capable of communicating with the civilization that built it. Current calculations suggest that, left undisturbed, Voyager 1 will continue drifting through interstellar space for genuinely astronomical stretches of time afterward, with one long-range projection indicating it will pass within a few light years of the star Gliese 445 in roughly 40,000 years, a genuinely staggering span of time to consider, for a machine that most people alive today will not live to see reach that distant encounter. It is worth being honest about exactly how much uncertainty still surrounds this entire timeline, since that honesty is precisely what separates a genuine, carefully managed engineering effort from simple, confident prediction. The Big Bang power procedure currently being tested represents a genuine attempt to extend Voyager 1's operational life beyond what the raw, unmodified power math alone would otherwise allow, and if it succeeds, the spacecraft could potentially continue transmitting usable scientific data for meaningfully longer than current projections currently assume. If it does not succeed, or if some other unexpected hardware failure occurs first, that timeline could just as easily shorten instead. Nobody currently knows for certain exactly how many more years of genuine two-way communication remain available with this specific spacecraft, and the engineers managing the mission have been consistently direct about that uncertainty, rather than offering false confidence about a precise end date. What remains completely certain, regardless of exactly how the coming years actually unfold, is the significance of what November 18th, 2026 genuinely represents. A machine built using technology that predates the personal computer, launched on a mission originally expected to last only a handful of years, running today on less electrical power than a single household light bulb, will become the first object built by human hands to sit a full light day away from the civilization that created it. Still, as of that exact moment, listening for commands. And still, when conditions allow, sending its faint 23-watt signal back across that entire growing gulf of space. Bolted to its frame, traveling alongside it through the same vast distance, sits the golden record, a message intended for whoever or whatever might eventually find it, long after Voyager 1 itself has gone permanently silent, carrying the sounds, images, and greetings of the civilization that once reached this far, and then, quite deliberately, decided to keep reaching further still. If you want to know exactly what happens when the Big Bang power procedure is finally attempted on Voyager 1, and whether its shutdown instruments can genuinely be brought back online, subscribe and turn on notifications, because this milestone is arriving in just a few months, and the spacecraft's next chapter is still actively being written, one carefully managed decision at a time.